Good morning, everyone. Hope you're all doing well. I just love this 130 classes. I love the students. It's the students that end up gravitating to this class. You guys are always just such good students, and um, it's great. And you guys, you ladies, guys, gentlemen, all of you, whoever, whatever your pronoun is, you've all been great. And one representation of that is that every single person took the first test. And I didn't get any emails and I didn't get any, oh, I missed the test. I didn't get it. Every single person in the class took the test. And you all did pretty well as also, so great. So I'm really happy about that. So let's just keep that going for the rest of the semester and I will be a happy teacher. So the next chapter that we're working on is a big chapter. There's a lot of information in it. Talks all about atoms, and elements and lots of things with the periodic chart. So if you could make sure that you have a copy of a periodic chart available, there is one in your lab manual. So if you want to use that one, that's fine too. Where are you? There's a couple of them. Yeah, so on the inner cover of your lab manual, there's one as well. So just have something available that you can write on. Yeah, tired this morning. All right, so what is an element? So an element is classified as what we call a pure substance. We can kind of take matter and divide it into either pure substances or mixtures, right? So it's a pure substance. It has a uniform composition. It's made of only one type of material or one type of atom. It can't be broken down into any simpler substances through chemical reactions. And they're everything that's listed on the periodic chart. So we have, roughly 118, something like that, 120 of these elements. Some elements are named after planets, some are named after places, some are named after people. Some of them are named after properties. So chlorine is named after the root chloros, which means green, yellowish, which is chlorine has this like sort of green, yellow, gaseous quality to it. So it gets a little cumbersome to write out the entire name of all of these things over and over. So if I'm trying to talk about carbon, I don't want to write carbon over and over. So instead, I'm going to use the symbol. So for carbon, it's C. Nitrogen and fluorine. You can see all these on the periodic chart. Some periodic charts give you the name and the symbol. The one on the inside of your lab manual only has the symbol, which kind of stinks when you're dealing with some of the ones that don't match up. All of these match up, right? Cobalt kind of makes sense that it would be CO, calcium, Ca. Here's a bunch of the symbols. Some of them don't make as much sense, like potassium is K. That's because its root is, or its Latin root is calcium. That's what it was originally named. Another one, iron, is Fe, because it used to be called ferrium. You may see things written on occasion in places where it says like ferric acid or ferric oxide. If you see the word ferrous, it's talking about iron. Just correlate those two. So you want to be able to, match the symbol with the right element. You don't want to use S for sodium. Okay, sodium, which I don't think is on here. Sodium is Na, sulfur is S. Silver, Ag, gold, Au. All right. I don't think we need to spend this much time, but it says write the correct symbol. Okay, so you want to be able to look at a periodic chart and reference and find the symbol. Yeah, we don't. It's a little too much. So carbon has the symbol C. The thing though is when I say, oh, it's carbon, I can actually mean a couple different things as far as what you would see on the macroscopic scale, because carbon's atoms are very unique and they can be arranged in a variety of ways. So one of those ways is to align carbon in sheets. So there's these little like hexagons, and they're attached in these planar sheets. And this would give you what's known as graphite. And graphite, because of this sort of sheet-like property, that's why you can write with graphite. It comes off in sheets and gives you this dark grayish color. Then you can also have carbon arranged in what's known as a framework structure. This is where instead of it being in these sheets, it's every single carbon is attached to a carbon around it. And they all have equal strength bonds, very, very strong, and you get a diamond. It can also be arranged in this sphere shape, and I'm not even going to try and say that name, but this sort of spherical shape, which is prominent in like nanotechnology. And then you've got, you could take something like this, which is like this graphite sheet, and fold it in on itself and get a nanotube. So don't just assume if it's carbon that it's one thing. It can be a variety of things. Some other things, mercury. Mercury, we talked about being a metal because it's to the lower left in the zigzag line, and it is the only one that is liquid at room temperature. Here's a pool of mercury. You would not want to get in there. It is very poisonous. All right. So here's our periodic chart. We're going to talk about the organization of this thing. So on the periodic table, elements are arranged according to similar properties. Even before that, on the periodic chart, elements are arranged by their mass. So you read the periodic chart like you would a book. You start in the upper left-hand corner, you go across a line or across a row, and then you come down to the next row. So this is 1, you go over here to 2, then you come here to 3, 4, 5, 6, and so on. And we go through this like a book. Okay, one thing to note, when you get to row 6, where it goes to 57, you jump down here to what's known as the lantholides, 58 through 71, and then you go back up to 72. Okay, so this thing inserts itself in there. Why don't they put it in there? There are some periodic charts that have that inserted in there. It just makes it very, very long, and it's not convenient to put on a sheet of paper. So they're in order of increasing atomic mass. So these things down here are going to be heavier than these things up here. So again, on the periodic chart, we have these things that are called, well, we have groups and we have periods. So groups contain elements with similar properties, and these are the vertical rows. So go to where hydrogen, lithium, sodium, potassium, that we would classify as group 1. All of those things minus hydrogen, because hydrogen is its own entity, they all have very similar properties. If you go to column 2, where beryllium, magnesium, calcium, strontium, barium are, those guys have very similar properties. That would be group 2, or we would call them the alkaline earth metals, and we'll get the names a little bit later. But so look at lithium and beryllium. So lithium is number 3, beryllium is number 4. They're right next to each other, right? Well, lithium is much more like cesium, which is 55, which is like a couple steps down. Lithium is much closer to cesium than it is to beryllium as far as properties are concerned. Okay, so don't assume, oh, it's sitting right next to something. It's got to be similar. Like helium and hydrogen could not be any more different from each other. You don't fill balloons with hydrogen, you fill them with helium. Periods are the rows that go across, and there are 7 periods. Starting with the first period is very small, it's just hydrogen and helium. 6 and 7 do include the lantholides, so you will want to insert those in there. There is no there's no property consistency within a period, okay? So when you move across, like let's say we look at period 4 where potassium, calcium, scandium is, so titanium, those guys are not similar to each other property-wise. And potassium, you know, if you jump all the way over to the other side, is in the same period as krypton. Those things, again, couldn't be more different than each other. So don't assume if they're in the same period that they're all gonna have the same properties. So here's our periodic chart. Here's group 1. When I'm talking about groups, I'm talking about main group, okay? So this group here, this one here, and then the 6 over here. So this is gonna be 1, 2, 3, 4, 5, 6, 7, 8. These things in the middle are known as transition elements. They have much more unpredictable charges. I would never say, oh, like the 5th row and the transition elements, because these guys have varying properties. They're not similar to each other in the way that our main groups are. As far as the main group elements are concerned, this first group are known as alkali metals. Second group is alkaline earth metals. The 7th group over here are the halogens. And then the 8th group at the very end are known as the noble gases. Your periodic chart should have a bolded in zigzag line. If it's not there or you can't see it, go ahead and highlight it or draw it in with a ballpoint pen. The zigzag line starts here on boron, cuts over and down all the way to the end. And you can kind of continue this like underneath hydrogen as well, because hydrogen would follow the same pattern. Anything to the left and down of the zigzag line is a metal. So there are lots of metals, and all these lantholides are also metals. So lots of metals on the periodic chart. Anything up and to the right of the zigzag line, those are going to be nonmetals, not quite as many. Then there are some of these things called metalloids, which have intermittent conductivity properties. So they can kind of behave like metals and not metals. And they go along the zigzag line, but leave off aluminum. Aluminum is definitely a metal. So most of what you see on the periodic chart are metals. So the group numbers, when you hear me calling out group numbers or columns, like, oh, group 6, I'm not talking about anything in the transition. I'm talking about the representative elements or the common elements or the more predictable elements. So group 6 would be the oxygen, sulfur, selenium group. Sometimes there is an alternative system where they number them truly 1 to 18, and they go, you know, group 1, group 2, group 3 would be that first transition metal. So it would be 1, 2, 3, 4, 5, all the way over to 18. I don't use that. This will be 1, this will be 2, and this will be 3, and so on. So you can kind of call out elements by their group and their period, like battleship, right? So calcium is in group 2 and period 4. So you can go over and down. We've got our alkali metals, our alkaline earth metals, our halogens and our noble gases. These do have group names. They're just not very common. We don't use them a whole lot. It looks like the periodic chart or periodic table that you have on your lab manual does have the names of those. If yours doesn't, if you have a periodic chart that doesn't have those, write it down because you will want to know, like, if I'm like, oh, I need a halogen that starts with B, you could be like, oh, bromine. So have that around. So here's our alkali metals. Lithium, sodium, potassium, rubidium, and cesium. We don't include hydrogen in that because hydrogen does its own thing. So one thing I want you to write above this column is a +1 or 1+. And that is because everything in this column, and we'll get more into ions later, but everything in this column likes to give up one electron and form a positively charged particle with a magnitude of 1. So why that's the case, we're not going to worry about that right now. You're just going to trust me that that's a +1. The halogens on the opposite end of the periodic chart, so column 7, a lot of those are gases, but some of them can be solid at room temperature. Above that column, I want you to write a -1 or a 1-. Because if something is giving up electrons, something in the universe has to be taking electrons on, right? Or we just have like an abundance of free electrons. So put a 1- above the halogens. Let's fill in the rest of these. So above this group here, I want you to put a 2+. So these guys like to form a 1+ charge. This column likes to form a 2+ charge. We said this is a 1-. This group here, 6, where we have oxygen and sulfur, that's a 2-. So they like to give up 2, or they like to take on 2 electrons. And then we'll stretch it into nitrogen and phosphorus, put a 3- there. Those guys like to give up 3 electrons. What about the noble gases? Well, noble gases, they're noble because they stay with their own kind. They don't like to do any bonding. The reason they don't like to bond is because they don't really form ions. So above this, you can put like a 0 or a 0 with a slash through it, or Na, or something that lets you know that those guys aren't going to ionize for bonding. Okay, so identify the element described for each of the following. I do want you to try this out. It should only take about 45 seconds to do each one. I want you to tell me what is what, just so that you can get comfortable with group and period. Okay, so 7a period 4. So that means we're going to go over to group 7, which is the halogens. And then we need to go down to period 4. There is no element that lives in period 1 for that group, but we still have to count it. So fluorine is actually starting at 2. So 2, 3, 4. So bromine should be our answer for that, okay? You don't want to take it all the way down to iodine. The next one, 2a, period 3. So go over to the second column. We count 1, 2, 3, it would be magnesium. Again, you don't want to take it all the way down to calcium. You have to kind of count the first step, even though nothing is there. And then group 5, period 2. So we go over to 5. 5 is the nitrogen phosphorus group. And if we're in period 2, well, we've got that phantom 1 and then right down into 2 for nitrogen. Not too bad. All right, so we already talked about this. Metals are located to the left of the periodic chart. Non-metals are to the right. Metalloids are along our zigzag line. There's our metalloids, everything but aluminum. Aluminum, just in your mind, okay, that's definitely a metal. Some properties of metals. Metals are shiny and ductile. They're good conductors of electricity and heat. Some other things, they're always, not always, but most of the time, they're solid at room temperature. One chance or opportunity where that doesn't happen is mercury, okay? Another thing you can write with metals is that they like to form cation ions. They also like to form this thing called a cation. And a cation is just a positive charge. Or they like to lose electrons to keep a positive charge. Remember, electrons are negative. So if you get rid of them, you become more positive. Nonmetals are usually dull and brittle, poor conductors of electricity, but they're good insulators. So because they don't conduct, they are good at blocking. We use them for insulation. Nonmetals have much more varying properties. They're not all solid at room temperature. They're just like more, just more varied. Okay, so oxygen and sulfur and chlorine are all around each other on the periodic chart. They're all nonmetals. They have a lot of different properties versus the metals over the left, they're a little bit more uniform. And we talked about this. So if metals are giving up electrons to form a cation, something has to be eating up those electrons, and that tends to be nonmetals. So nonmetals like to form what's known as an anion. And an anion is just a negatively charged particle. Okay, so these guys give electrons, these guys take electrons. Metalloids are better conductors than nonmetals, but not as good as metals, which is great because they're semiconductors. You can kind of control their conductivity, turn it on and off like a switch, which is really great for electronics. We don't call Silicon Valley Iron Valley, right? Or a real solid metal. We call it Silicon Valley because silicon is a metalloid that's really great for electronics. Here are some other just properties of things: metal, non-metal, metalloid. Metals in general tend to have a higher density than non-metals. Yeah. All right, so identify the following elements as metal, non-metal, or metalloid. I want you to actually go through and do this. You don't have to write it down, but just real quick, go through and say that's a metal, that's a non-metal, whatever. Because this is so important for naming and writing compounds, that if you can't identify something as simple as it being a metal or non-metal, it's going to give you trouble down the road. Just 30 seconds. Okay, so that first one, sodium, it's definitely a metal. It's sitting over to the left. Chlorine is a non-metal, it's up to the right. Silicon, we said, was a metalloid. I don't do a whole lot with like metalloids as far as compounds are concerned, so you probably won't need to be identifying those very often, but we would say that's a metalloid. Iron, definitely a metal just from where it's sitting in the periodic chart. Carbon, non-metal, again, because of where it's sitting on the periodic chart. So just go off of, is it to the left of the zigzag or to the right? All right, we're not gonna get through that. So just some information about elements. Of all the elements, 20 are essential for survival of the human body. The 4 elements that are most important for body mass and make up like 96% of what we would classify as our body mass, not water, but the other stuff, is oxygen, carbon, and hydrogen and nitrogen. We've got these things called macro minerals. So there are, not all of them, but a lot of them are metals. We've got sulfur and chlorine in there. These are good, not just good, they're necessary for the formation of things like teeth and bones, maintain your heart and your vascular system and metabolism regulation. So, you know, you need to be getting, like we eat salt. We need to eat salt because we have to have a correct level of Na and Cl in our system. So here you can see the things that are sort of essential for our bodies. There are these things called microminerals or trace elements that we do have in small quantities. So we do have small quantities of iron in our system and cobalt. We don't want to have those in really large quantities though. And then all this other stuff is just not something we want to have in our bodies. So now that we have a little bit of a better working knowledge of how the periodic chart is set up, each one of those boxes is representing a different element. The most fundamental thing of an element is an atom. So if I've got this aluminum foil here and I zoom into a little section, you can see that it'll be these little, what appear to be little balls of an aluminum atom. An atom is the smallest particle of any element that still retains the characteristics of the element. So it's like, if you want to still classify it as aluminum, like how many times can you cut aluminum up and it's still aluminum? You can cut it up all the way down to the atom. If I was to somehow slice the atom in half, the aluminum atom, it would no longer be aluminum. That would be the point where we have moved into something else. So some theories on atoms, Dalton's atomic theory. This was postulated in the 1800s. He thought that atoms were tiny particles of matter. So we had these little balls of matter. Every atom of an element are similar to each other and then different from other elements' atoms. So all copper atoms are like each other. And they're all similarly different to carbon atoms. Each atom will combine with other elements to form what's known as a compound. So when I'm talking about a compound, it's like when two atoms have gotten together in some sort of fused relationship. And you can rearrange atoms in a bunch of different ways to form new things through chemical reactions. So, when we have, let's say, water, which is hydrogen and oxygen, H2O, those guys aren't fused for life. They can break up. The hydrogens can break from the oxygens and then go and bond with something else and form a new compound. And during a chemical reaction, atoms are not ever created or destroyed. So we're never going to just the atom just disappeared. The aluminum just disappeared. That doesn't happen, at least within a chemical reaction. In nuclear reactions, atoms do shift and change into energy. And we'll talk about that in chapter 8, sometime in the future. So if you break up an atom, it has these subatomic particles, sub meaning smaller or less than, atomic less than the atom. So subatomic particles, 3 of them, protons, electrons, and neutrons. So every element will have protons and electrons, and then they should have neutrons. Sometimes they don't. For instance, hydrogen doesn't have a neutron. It's really just a proton with an electron floating around it. So what are the properties of these subatomic particles? Protons, P for positive. So protons have a positive charge. Positive things repel each other. Electrons have a negative charge. Negative things repel each other. Likes repel, differences attract. So positive and negative like to stick together. So that's why the electrons, which rotate around the nucleus, stay around, because the protons have a pull on them. It's not a gravitational pull, it's an electromagnetic pull, but yeah, they hold them close. Then you've got these things called neutrons, and they're neutral. They don't have a charge. So they're cool sitting by whatever. So Dalton didn't really know about these subatomic particles. Dalton just was thinking that atoms were just these sort of hard, tiny balls of matter. The subatomic particles came later. The first particle to be discovered of those 3 was actually the electron. So they found the electron first. This guy, J.J. Thomson, had this cathode ray experiment. And what he found was that when he ran atoms next to it, these negatively charged particles would come off of it. And he discovered that they were, in fact, electrons. They had a much smaller mass than the atom themselves. So he was seeing, okay, these things don't hold a lot of mass, but there's definitely a charge. So he proposed this thing called the plum pudding model. Here's the plum pudding model. He thought instead of the atom being this hard, solid ball, it is made up of tiny little electrons that have a negative charge, and then there's a positive like pudding or like a cloud of positivity that is counteracting the negative charge. Because in general, unless we're looking at an ion, atoms have a neutral charge. So he had no idea about the nucleus. This was just his hypothesis. Well, later on, this guy Rutherford ran what's called the gold foil experiment. These are all like really, really classic chemistry experiments. And what he did was he shot alpha particles at a really thin piece of gold, like just a couple atoms thick. And if it was the plum pudding model, the alpha particles, because they're so high energy, they should just go straight through the atom. And what he found was that when he shot the particles, some of them went straight through, but some of them actually deflected. Some of them almost came all the way back. This piece of rounded fluorescent screen here, it lights up when an alpha particle hits it. So it's really easy to see where the alpha particle has been. So he found that there's all these deflected particles. Well, why is that happening? Well, he came up with this idea that there must be something really dense in the middle of our atom to be causing that sort of deflection. It's got to hold all the mass of the atom. And that is where he came up with the nucleus. So now we have the nuclear theory, or the nuclear understanding of the atom. In the nucleus, so here we've got lithium, then we've got lithium atoms. If I break the lithium atom up, or if I zoom in to one of these lithium atoms, we'll see that there's a nucleus in the center, a bunch of empty space, and then these little tiny electrons, okay? And if we zoom into the nucleus is gonna contain all of the protons and all of the neutrons. So protons and neutrons hang out in the nucleus. Electrons occupy most of the space around the atom. So most of the size of what we consider an atom to be is actually just electrons floating around in empty space. So when measuring the mass of an atom or subatomic particles, we use this thing called an AMU because grams are so tiny, or these are so tiny that grams would be too big for that. So an AMU is equal to 1/12 of the mass of a carbon atom. And if it's carbon 12, that would be the mass of a proton. So a proton has a mass of about 1 AMU. A neutron also has a mass of about 1 AMU. It's slightly heavier, but protons and neutrons have a very similar mass. We just kind of consider them as being a mass of 1. An electron, on the other hand, look how much smaller this is, 0.000549 AMU. So they do have a mass, but it's about a 2,000th of a proton or a neutron. So not much mass contribution. When we talk about the mass of an atom, we're really just talking about adding the protons and the neutrons. We leave the electrons off. But we don't want to forget about the electrons because they hold a lot of bang for their buck, right? They have a negative charge, and that's why like bonding for compounds even happens. So some of the properties of these subatomic particles, you want to know this. Protons are positive, neutrons are neutral, electrons are negative. Know that the mass of a proton is 1, the mass of a neutron is 1, the mass of an electron, you can just say is negligible, okay? And also know where they're located. Any questions on the setup of the atom and the subatomic particles? There's only 3 of them that you need to know. You can break these things down. You can break protons and neutrons and electrons down into even smaller things. smaller subatomic particles, which are called quarks, and they start getting really funky and doing crazy funky things. So that leads more into physics. All right, so which of the following subatomic particles fits the description below? So it's found outside the nucleus. Only electrons are found outside the nucleus. Has a positive charge. Only protons are going to be positive. Has a mass, but has no charge. Neutrons. So when classifying an atom as like a specific element, like why is carbon carbon and it's not oxygen? That all has to do with something called its atomic number. So the atomic number is the big whole number that's sitting at the top of the box. Usually it's in the upper left-hand corner, just sitting above the symbol. That atomic number tells you how many protons are in the nucleus. So hydrogen has 1 proton. Gallium, number 31, has 31 protons. The number of protons is synonymous with the element. So if you're going to be gallium, you have to have 31 protons. We can kind of mess around with the number of electrons and we can change the number of neutrons if we're an isotope. We cannot change the number of protons. If you change the number of protons, you are now a different element. So looking here, every single atom of lithium has 3 protons. If we are looking at carbon, every atom of carbon will have 6 protons. It's always a whole number, and it appears above the symbol. So yeah, it looks like the 2 that I'm looking at have it just sitting right above the symbol. Sometimes it's in the corner. So kind of really beating a dead horse here, but the atomic number is the number of protons. And that will always be synonymous with the symbol. So carbon will always have protons that are 6, right? Copper will always have 29. So it's really easy to find the number of protons. If I say, hey, we're looking at aluminum, how many protons does it have? It's real easy. You just look down at the periodic chart, you see aluminum is number 13, so it's got 13 protons. Now for a neutral atom, so not a charged cation or an anion, a neutral atom has a charge of 0. What charge do protons have? They're a positive charge. What charge do electrons have? A negative charge. If we want to be neutral, that means the number of protons will equal the number of electrons. So if I say, hey, I'm looking at aluminum and it's neutral, you know that it has 13 protons, and then you also automatically know that it has 13 electrons, right? The positive needs to equal the negative. So protons, look at the periodic chart. Electrons, if it's neutral, you just assume it's the same as the protons. All right, so go ahead and do this right here. Just do the first one. We don't need to do all 3. So nitrogen, what is its atomic number? How many protons does it have? And how many electrons does it have? Okay, so nitrogen is, we find that on our periodic chart. Hopefully the more you use your periodic chart, the easier it's gonna be to look these up fast. It's got an atomic number of 7. So how many protons does it have? 7. How many electrons does it have? Well, it's not charged, so it also has 7. So all these are gonna be the same. Zinc is a little bit heavier with 30, 30, 30. Sulfur, 16, 16, 16. The mass number. So the atomic number is telling me the number of protons. The mass number is telling me the mass of the whole atom as a unit. The mass number is going to equal the number of protons plus the number of neutrons. Okay, so you may want to write out a little equation for yourself there that says mass number equals P plus N, protons plus neutrons. It's a whole number because protons have a 1 and neutrons have a 1. It doesn't appear on the periodic chart in that, do you guys see the decimal number underneath each of the elements? That is the average mass number. So that's the mass number of all the isotopes combined together. That's not telling us about a specific element. So we're looking at like carbon 12, we're using the 12 mass. We're looking at carbon 14, we're going to use a 14 mass. And we'll get a little bit more into that. So do we see electrons anywhere in this equation? No, we don't include electrons for the mass. All right, so hydrogen, H, has an atomic number of 1. It has a mass number of 1 as well. So the whole mass weighs 1. Well, the number of protons is 1. That means the number of neutrons will be 0 because the mass number is protons plus neutrons. Number of electrons here would be 1. Let's look at a bigger one, iron. Iron has the symbol Fe. If you look at your periodic chart, iron has an atomic number of 26. The mass number for this specific iron, we're going to say that this is iron 58. All right, the mass number has to equal protons plus neutrons. So if you have the mass number, you have the atomic number as 26. We know protons have to be 26, right? This number here and this are the same. We take our 58, we minus the 26, we get a remainder of 32 neutrons. So for iron 58, we would have 32 neutrons. Number of electrons, we're going to say is the same as protons, 26, because it isn't charged. All right, so here are some study tips. Protons is the atomic number. Protons and neutrons is the mass number. Neutrons, we can rearrange this equation because a lot of times you're having to calculate the neutrons is equal to your mass number minus your atomic number or minus the number of protons. So let's look at this one. An atom of lead has a mass of 207. I want you to tell me the protons, the neutrons, and the electrons. I'll give you just a minute. Okay. So if it's lead, we have to find it on the periodic chart. Where are you, lead? All right, it's number 82. So it has 82 protons. Easy to figure out. Its atomic mass is 207 because that was given to you. So in order to figure out the number of neutrons, we're going to take the mass, 207, we're going to strip away the protons. So we're going to subtract the protons, which are 82, and we should end up with 125 neutrons. How many electrons? Well, there's no charge to it. It's just regular neutral lead. So the protons and the electrons should equal each other, and we should also have 82 electrons. Any questions on calculating the number of subatomic particles? You will definitely want to be able to do that. You're going to need to know how to do protons, neutrons, and electrons, calculate them, especially because in this class, we do a section on nuclear chemistry. So we do a lot with the nucleus. Okay. So let's move forward. Isotopes and atomic mass. So what is an isotope? An isotope is an atom that's the same element, but it has a different mass number. Well, if it's the same element, it has to have the same number of protons. Two isotopes will have the same number of protons because they have relatively the same properties. But if it has a different mass, we change the number of neutrons. So you can have situations where you have more or less neutrons. Does that affect the charge? No. Does it affect the identity? No. It only affects the mass. So if we look at this one here, magnesium, this would be magnesium, and I would call this magnesium 24. So it's Mg, it has a mass number of 24, its atomic number is 12. This is always like going to be 12. If it's magnesium, it's always going to be 12. But in this individual isotope, we're dealing with magnesium 24. Let's look at a couple of these here. So this is a lot of times how you'll see it written. You'll see the symbol in the upper left-hand corner will be the mass. In the lower left-hand corner will be the atomic number. Again, this is sort of fused together with the symbol. That's not going to change. If this is an O, this bottom thing will always be 8. So I would call this thing oxygen 16. If I'm working with oxygen 16, it should have 8 protons because its atomic number is 8. It will also have 8 neutrons because the mass is 16. I'm going to take 16 minus the 8 to give me the remainder of 8. And then the electrons will also be 8 because it's charge neutral. Don't always assume, some people say, well, isn't the number of neutrons equal to the number of protons? No, not always. Look at this one here with phosphorus. So phosphorus 31, if it's phosphorus, it has to have 15 protons. That's a sealed deal. Because it's 31, we're going to take 31 minus the 15. The number of neutrons in this case is actually 16. The number of electrons will be 15. Let's go to something that's even heavier, zinc, and this is zinc 65. So 30 protons because it's zinc. The number of neutrons is 65 minus the 30 to give me 35 neutrons. The number of electrons will be the same as the protons, so 30 electrons. So as your elements get heavier, you'll see that the number of protons increases by 1, but the mass will increase by a larger factor. So you start to pack in a lot more neutrons as you get bigger. Some of those bigger elements have a lot of neutrons. That's why they tend to be a little bit more unstable. The nucleus gets a little clunky. So let's compare a couple different isotopes. When I'm looking at magnesium, this is magnesium ribbon. If you've ever burned magnesium ribbon in a chem class, it's kind of fun. It burns this really bright color. But this magnesium ribbon will have a certain percentage of magnesium 24. It'll have magnesium 25, and it'll have magnesium 26. Notice the symbol is staying the same because they're all magnesium because they all contain 12 protons. But the atom is getting slightly heavier. Why is it getting heavier? Because it's adding some neutrons. So magnesium 24 will have 12 protons. Hey, magnesium 25 also has 12 protons, and so does 26. Those are all 12. What shifts as this thing becomes heavier is that we start tacking on more neutrons. So this has 12 neutrons, this has 13 neutrons, and this has 14 neutrons. Now, each of these exists in a certain abundance in nature. So most of the magnesium out there is magnesium 24. That's about 78.7%. They've found this experimentally, if you're wondering where that number comes from. Magnesium 25 is about 10%, and magnesium 26 is roughly 11%. So most of it is magnesium 24. So if you go to your periodic chart, do you see how in the magnesium box, it's 24.3050. It's not exactly 24. That number is coming from taking the average of all of the isotopes. If you've ever calculated a grade in a class where tests were worth the most, right? So the tests were worth 60%, homework was worth 20%. So you had to average it out by using the percent abundance or the percentage. It's the same thing. They take, this mass and they multiply it by the percentage. They take this mass and multiply it by its relative percentage and so on, and then they add them together. So we will do some calculations with that. But for now, I want you to look at this. We have carbon 12, carbon 13, and carbon 14. I want you to tell me protons, neutrons, and electrons for each of these isotopes. It doesn't give you the atomic number in the lower left-hand corner. Just look it up on the periodic chart. Okay, so for each of these isotopes, if it is carbon, protons, 6, 6, 6. Electrons, because we know when it doesn't have a charge, and we'll talk about that charge in the upper right-hand corner, so just assume as of now it's neutral. Protons and electrons equal each other, so this will also be 6, 6, 6. Neutrons are going to be what shift. So you want to take your atomic number, or your atomic mass rather, and subtract it from the atomic number, or the protons. So 12 minus 6 will give me a remainder of 6. Carbon 13, we subtract out 6 for the protons, we end up with a remaining of 7. Carbon 14, which is the heaviest, and this is also a radioactive isotope, it likes to decay, so we use it for aging things. Subtract the 6, and we get 8 neutrons. Now these have their own abundances. Most of the carbon out there is carbon 12, a small sliver of it is 14 and 13. So we would average those together, and that's why the number on the periodic chart is not exactly 12, it's 12.011. All right, so I want you to try this. Write the atomic symbol for the atom with the following subatomic particles. So I want you to write the symbol along with the mass, like how this would be like carbon 12. Okay. All right, so if we have 8 protons, it has to be oxygen. We can put the little 8 on the bottom, or you can leave the 8 off. It's, it's not necessary. But you do need to put the atomic mass in the upper left-hand corner because you have to tell me what oxygen are you dealing with. And in this case, it's oxygen 16 because the 8 and the 8 will total the 16. In this one, we are dealing with chlorine 37. Chlorine 37, 17 protons because it's chlorine, and then the remaining 20 will go to the neutrons. This would be silver 107, so they start to get heavier. Silver always has 47 protons. In this case, it has 60 neutrons. So you can start to see as things get heavier, that number of neutrons starts to skyrocket, right? At one point, neutrons and protons were equal to each other for the most part. Now we're definitely increasing a lot. In which of the pairs are isotopes the same element? In which of the pairs do both atoms have 8 neutrons? Okay, so I'll go over this. So looking at these pairs, which of the pairs is the same element? B, 6 and 6, right? These both have 6 protons, so it would be carbon. Which one has the same, or which one has 8 neutrons? So you would have to go through and subtract each of these in order to do that. And it's going to be C. So 15 minus 7 and 16 minus 8. In both those cases, that equals 8. So we have 8 neutrons. They're different materials, but they both have 8 neutrons. So calculating the average atomic mass on the periodic chart, again, I've said this number here, like if we look at chlorine, that 35.45 is a combination of chlorine 35 and chlorine 37. Because the number sits closer to 35, you can assume that the chlorine 35 is going to make up a larger percentage, and that is true. Chlorine 35 makes up about 75.76%. The remaining quarter is chlorine. I don't expect you to have percentages of these things memorized. That would be something I would give to you. But we are going to calculate the weighted average for all the naturally occurring isotopes. So the equation for this, come on, does it have it written out somewhere? It's like it doesn't have a specific way. Okay, so you take the percentage abundance of each isotope, you multiply the percentage abundance by the atomic mass that it's associated with for the isotope, and then you sum them all together. I wish they had some, they don't. Okay, I'm gonna just write something down. So this is how the formula is going to go. It's going to go abundance 1 times isotope mass 1 plus abundance 2 times isotope mass 2 plus, let's go abundance 3 times isotope mass 3. And then I'm going to put a dot, 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 dot. Because you could have 16 isotopes and you just sort of have to keep the process going. So this first part, this abundance, you're gonna take whatever your percent is. So take percent and divide it by 100. Why? It's a way for us to get out of percentage and into decimal. This over here, the isotope mass, this will be given. And in parentheses, say use specific number if available. So sometimes they'll say, hey, chlorine 35, but it's really 34.9992. Use that more decimaled version of this. And we'll do a couple examples. So you just got to go through each of them and add them together. So let's look at what they had going on for chlorine. So chlorine 35, chlorine has two isotopes, chlorine 35 and chlorine 37. It's 3/4 and 1/4. So what we're going to do is take whatever our percentage is, divide it by 100, multiply it by the mass, plus the other isotope, divided by 100, the percentage, and multiplied by the mass. So for chlorine 35, the mass is actually 34.97. So anytime they give you a more detailed mass, use the more detailed mass. If they didn't give this to you, you would just use the 35. All right, you could just use plain 35. But because they're giving us something that says, no, it's really 34.97, use that. So we're going to take that mass and we're going to multiply it by its relative abundance. In this case, the chlorine 35 makes up 75.76%, but we have to divide it by 100. We have to get it out of percentage. Another thing you can do instead of dividing it by 100 is just move the decimal over 2 places. It's a little faster. So what we find is that when we take 34.97 and we multiply it by the 0.7576, we get this thing right here. We get 26.49 AMU. So 26.49 AMU is coming from the chlorine 35. Then we have to do the same thing for the second isotope. So chlorine 37, how do you get the 75.76%? That will be given to you, all right? So abundances will be given. How are they, where do they come from? Like, did we just make them up? No, scientists meticulously went through samples of chlorine and they consistently came up with these percentages, all right? So I won't expect you to have those memorized. So second line here, we've got chlorine 37, which is actually 36.97. So we're going to use that times the percentage, which is 24.24 divided by 100, or move the decimal over 2 spots. And we get that the remainder contribution is 8.9625 AMU. Now we have to add these two things together because these don't look anything like the original number, right? This is 35, this is 37. This thing isn't falling anywhere near that. But when we add them together, what happens is we get an average of 35.45. This final number that you come up with better sit between your 2 isotope masses. If your final number is greater than 37 or less than 35, you've done something wrong. If you're getting A's on tests and you're getting C's on homework, it wouldn't make sense for you to have a D in the class. That falls outside of the range of the average. So here are some different isotopes that are out there. Lithium has 2 isotopes. When you average those together, you get isotope or an atomic mass of 6.941. The most prevalent isotope, because this is 6.941, what number is that really, really close to? It's really close to 7. So we would say we're going to have more of that than this. It's just something you can kind of infer. Here's all of our carbons, 3 different isotopes, but the average atomic mass is 12.01. Which one do we expect to see the most often? Carbon 12. Oxygen is 16 AMU, almost on the dot. So we really have very small amounts of 17 and 18. 16 is the most common. Let's see. Oh, 908. Okay, yeah, we're going to stop there. We'll do one of these problems next time. I'm going to calculate out some average masses. So have a good day. Thank you so much for finishing your test on time. I know some people have been emailing me about meeting up or having questions or things like that. So feel free to stay around if you've got a free minute and we can talk. Otherwise, I will see you on Thursday. Bye, everybody.
Have a good day.
You too. Bye, Sarah.